This video looks at the reaction between potassium permanganate and glycerin. So our reactants are KMnO4, which is potassium permanganate, and C3H5OH3, which is glycerin. Potassium permanganate is a purple solid, and glycerin is a clear, very viscous liquid. Several reactions take place when the two are combined, but the one we'll be looking at today produces a potassium-based solid, a manganese-based solid, carbon dioxide gas, and water vapor. This reaction can be classified as an oxidation-reduction reaction. Let's look at the oxidation numbers of the manganese-based reactant and manganese-based product. The potassium ion has a +1 charge, so we know that the oxidation number of potassium is +1. Also, we know that oxygen will have an oxidation number of -2, and that there are 4 oxygens in the molecules. So to make the sum of the oxidation numbers equal to 0, we know that manganese has to have an oxidation number of +7. Now let's look at the product, Mn2O3. We know that oxygen still has to have an oxidation number of -2, and that there are 3 oxygens in each molecule. So, to make the sum of the oxidation numbers equal to 0, manganese needs an oxidation number of +3, since there are 2 atoms in each molecule. As you can see, the reaction reduces the oxidation number of manganese from +7 to +3. Since the oxidation number decreases over the course of the reaction, we say that KMnO4 is reduced, which means that it gains electrons over the course of the reaction. For KMnO4 to be reduced, we know that glycerin has to donate electrons, which means that it is oxidized. Now let's observe the reaction. We place 5 grams of KMnO4 in an evaporating dish and add 1 milliliter of glycerol. Initially, no visible reaction occurs. After about a minute, white vapor appears. Eventually, the reaction vessel begins to emit a purple flame. The fact that this process is an exothermic reaction explains why we observe this flame. In this reaction, delta H, or change in enthalpy, is negative, which means that heat is released into the environment. We observe this release of energy as a flame, and because potassium is a reactant, the flame appears purple. The rate of reaction is relatively slow, which is why it takes us so long to observe the purple flame. One way we could increase the rate of reaction to see the flame sooner is by changing the surface area of the KMnO4. Collision theory states that in order to have a reaction, the KMnO4 and the glycerin must collide at the proper speed and orientation to produce a product. When we observe the reaction, we use KMnO4 that was packed together tightly in crystals with small surface areas. This meant that the liquid glycerol molecules could only reach the KMnO4 that was on the outside of the crystal, and could not reach the molecules that were inside the crystal. Now imagine if we separated the crystal into smaller crystals of 4 molecules each. Now the KMnO4 has a greater surface area, so the glycerol molecules can immediately reach and react with every molecule of KMnO4. With more collisions, more products are produced faster, and the rate of reaction increases. Let's observe the reaction again. This time, we'll use a mortar and pestle to break up the KMnO4 crystals into smaller crystals, increasing its surface area. Again, we add 1 milliliter of glycerin to 5 grams of crushed KMnO4. The vapor and flame appear much sooner.